Array-based lists. In this session, you will learn about lists, explore how various operations such as search, insert, and remove on lists are implemented. Learn how to design and implement a generic class to process various types of lists. Become aware of the class vector. A local hardware store is about to open and needs to maintain a list of the items it sells. For each item sold, the list contains the name of the item, an identification number, the price of the item, the number of pieces of the item currently in stock, and so on. Like the list of items sold by the hardware store, we come across various types of lists. For example, we might have a list consisting of employee data, a list of student data, a list of sales data, or a list of rental properties. One thing common to all lists is that all the elements of a list are of the same type. More formally, we can define a list as follows. A list is a collection of elements of the same type. The length of a list is the number of elements in the list. Let us further consider the list of items sold by the hardware store. If a particular item is discontinued or the store does not sell the item, it is removed from the list. If a new item is available for sale, it is added to the list. Any item and any time an item is sold, the remaining number of pieces in stock must be updated. If an item goes on sale, its sale price must be updated. All these operations require you to access the elements of the list. As you can see, there are various types of operations performed on a list. Typically, the operations performed on a list are as follows. Create the list. The list is initialized to an empty state. Determine whether the list is empty. Determine whether the list is full, find the size of the list, clear the list, determine whether an item is the same as a given list element, insert an item in the list at the specified location, remove an item from the list at the specified location, replace an item at a specified location with another item, retrieve an item from the list from the specified location, search the list for a given item. Before discussing how to implement these operations, we must first decide how to store the list in the computer's memory. Because all the elements of a list are of the same type, an effective, convenient, and common way to process a list is to store it in an array. Initially, the size of the array holding the list elements is usually larger than the number of elements in the list, so that at a later stage, the list can grow to a specific size. Thus, we must know how full the array is. That is, we must keep track of the number of list elements stored in the array. Java allows the programmer to create dynamic arrays. Therefore, we leave it for the user to specify the size of the array. The size of the array can be specified when a list object is declared. It follows that in order to maintain and process the list in an array, we need the following three variables. The array list holding the list elements. A variable length to store the length of the list, that is, the number of list elements currently in the array. A variable max size to store the size of the array, that is, the maximum number of elements that can be stored in the array. We will design the class ArrayList class to implement a list in a program. This class will have at least three instance variables: list, length, and max size, as described in the preceding lists. Type of list elements. The variable's length, indicating the number of elements in the list, and max size, indicating the maximum number of elements that can be stored in the list, as defined in this section, are non-negative integers, and therefore we can declare them to be of the type int. What about the type of the array? That is, the data type of the array elements. If we have a list of numbers, Then the array elements could be of the type int or double. If we have a list of names, then the array elements are of the type string. Similarly, if we have a list of students, then the array elements are of the type student. We therefore see that there are various types of lists. A list such as of sales data or student data is empty if its length is zero. To insert an item at the end of a list of any type requires us to add the element after the current last element and then increment the length by 1. Similarly, it can be seen that for the most part, the algorithms to implement operations in a list of names or a list of sales data or a list of student data are the same. We do not wish to spend time and effort to develop separate code for each type of list we encounter. Instead, we want to develop a generic code that can be used to implement any type of list in a program. In other words, while designing the algorithms, we do not want to be concerned whether we are processing a list of numbers, a list of names, or a list of student data. However, while illustrating a particular operation, we will consider a specific type of list. To develop generic algorithms to implement list operations, we use the following facts. A subclass object in Java can be regarded as a superclass object. The binding of methods takes place at execution time. That is, binding of methods is dynamic. The class object directly or indirectly becomes a superclass of every class in Java, whether user defined or built in. Therefore, a reference variable of object type can refer to any object of any class. While writing the algorithms to implement list operations, we could think of list elements as objects of the type object. In order to use the list to store and manipulate data, the user can organize the list in the form of a Java class and, among other things, provide the basic operations on the data, such as comparing two data elements, copying data of one object into another object, and so on. The class object contains the method equals to compare two objects for equality, and the method clone, which returns a reference of a copy of an object. However, the class object does not contain any method to compare two objects for a less than or greater than relationship. Certain list operations, such as searching an ordered list for a specific item, require the less than or greater than comparison. In order to force the class organizing specific data to provide at least the following operations on the data: compare two objects for equality, compare two objects for less than or greater than relationship, make a copy of another object's data, return a reference to a copy of an object's data. We create an abstract class data element as described in this section. Items 3 and 4 ensure that the shallow copying of data is avoided. Recall that objects of an abstract class cannot be instantiated. While writing the algorithms to implement list operations, we assume that every list element is an object of the type data element. To organize specific data, the user can extend the definition of the class data element. In other words, the class data element becomes the superclass of every class, specifying the data type of the list elements. The following statements define data element to be an abstract class with operations described previously. Public abstract class data element. Inside it, we have public abstract boolean equals accepting data element other element. This method determines whether two objects contain the same data. and returns true if this object contains the same data as the object other elements. Otherwise, it returns false. Second, we have public abstract int compared to with parameters data element other element. This method is used to compare two objects. It will return a value less than 0 if this object is less than the object other element. It returns 0 if this object is the same as the object other element. It returns a value greater than 0 if this object is greater than the object other element. Third, we have a public abstract void make copy, accepting data element other element. This method is used to copy other element into this object. Post condition, the data of other element is copied into this object. Fourth, we have a public abstract data element get copy. This method returns a copy of this object. A copy of this object is created and the reference of this copy is returned. Figure 2-1 shows the UML diagram of the class data element. Notice that there are four methods as described in our data element abstract class. We have first the equals, second compare to, third make copy, and fourth get copy. Recall that the make copy and get copies definition are already described in our previous videos. Class int element. Suppose that you need to implement a list of integers in a program. The following class defines the data element to be of the type int. Public class int element extends data element. Protected int num. We have default constructor public int element, which sets the variable num to 0. Second constructor with parameters int x, which sets the variable num equals to x. Third, we have a copy constructor, public int element, accepting int element other element. This sets the num to be equals to other element dot num. Next, we have a method to set the value of the instance variable num. This method is called setNum and it accepts int x, which this method sets the value of num to be equals to x. Next method we have return it. This method returns the value of the instance variable num. So we have the definition int get num return num. Next method, we have the equals, which returns a Boolean value and accepts data element other element. We have created a temp here for the other element as int element. And then we return a value evaluating the condition if num is equals temp.num. Next, we have the method compare to accepting data element other element. Again, we created the temp variable as int element. This comes from other element and it is cast or converted into int element since other element is a data element. It has to be converted into int element because the num is compared to the num of temp and it is the num is declared as integer, so we return here the value as evaluated by num minus temp.num. Next, we have the make copy method as described previously. This method, we have accepted data element, other element, and we created again a temporary variable, temp, declared as int element, coming from other element, converted from data element to int element, and then we have a value num equals temp.num. In short, we are just making a copy of the temp's num to num, or to this object's num. Next, we have public data element get copy. So here we created again another temporary variable temp as a new int element with num as its initial value. And then we return the temp. So we're just creating a copy. We're just returning the copy of the object. Next, we have the public string toString that will return the string value of our num. This figure 2-2 shows the UML diagram of the class int element and the inheritance hierarchy. As you can notice, the int element um, is a subclass of the superclass data element, which means that int element inherits from the data element class. Similarly, you can create the class double element to implement a list of decimal numbers, such as sales data. Next, we have the class string element. If you need to implement a list of names in a program, you can create the class string element as follows. Public class string element extends data element. We put here the extends data element because string element is um, inherits or is a subclass of data element. So we have here protected string strs, its instance variable, and default constructor string element, which sets the str string equals to null or empty string. Public string element as our constructor with parameters string s, which sets str equals to s. Next, we have a copy constructor, public string element, accepts string element, other string str equals other string dot str that sets the other strings str to as the value to be assigned to str. Next method we have the set string. This sets the value of the instance variable str. Then it will give us a value of x assigned to str. Next method, we have the equals, the same as our method equals a while ago, but this time it is in a data type string. So we convert other elements, data element type to string element, and then we compare it. Next method is the compare to. The same a while ago, but this time it has a string element. Then we also have the make copy and the get copy and the toString method. Figure 2-3 shows the UML diagram of the class string element and the inheritance hierarchy.